He did all of the work in this for this paper. My name is Ben Mikek. Unfortunately, he couldn't be here, but I'll do my best to be a maximal under-approximation of the talk Shuo would have given. So C++ function templates look like this. They're an important feature if we want to constrain the types of inputs to functions. And so here, for example, we have a function f that takes x of type t. And for example, in this function, we can see that things of type t need to support the dump function call that's used inside this for loop. Unfortunately, if we call a function with a type that doesn't fit the type parameter that we expect, we get a very long and unhelpful error message. So here, if we call f with a null pointer, we get this error message that says that there's no matching constructor found. It's difficult to determine what went wrong based on this error message. And it goes on for 48 more lines after this. So clearly, this is a problem. After C++20, we got a new, better way of constraining types. So here you can see a type template where we have the concept of an integral constraining the type parameter t. If we try to break this again in the same way by calling it with a null pointer, we see a much shorter error message that only has 8 more lines that aren't shown. But more importantly, it tells us that there's no matching function call to f. So this is much more helpful in describing what the problem is and allowing a developer to try to fix the problem that's based on type parameters. So in C++20, all the problems in the world have been fixed. We have better interface specifications, we have better compilation error reporting, and we have better overloading control. But there's one problem with this picture. Programmers still have to manually write all of the constraints. And here's an example of a concept where a programmer will need to manually specify what this type t can be. In here, we want that things of type t support addition, and the result of adding two t's together should also be a t. And second, things of type t need to support the dump function call. And then, after that, we still need to see that we still need to put in place this function template where we say that things of type t need to either be of this concept int class or an std integral. So just to constrain this simple type t for this function g, we've had to write like 10 lines of code. And if we needed to do this for a more complex function, you can imagine this burden is growing pretty quickly. It grows even more quickly if we consider that we might have to do this for a bunch of legacy code bases that don't yet have type annotations. And so in this work, the problem that we face is that we want to automatically synthesize these function type parameters, the constraints on the type parameters, in order to reduce the developer workload and enable the introduction of these type parameters in legacy code bases that don't currently have them. So we want to infer the type parameter constraints for existing function templates. I'm going to summarize the method that's followed here in this paper in 3 simple steps. So first, if we look at a function, we're going to collect, if we look at a function that has a type parameter on one of its variables, we're going to collect all of the uses of that variable and encode each one as a constraint. So for example, in this function, we have x, which is of type u, and we see here that we call x.print. And so we're going to assign a constraint that x needs to support the print function call. We have a second call to x.print that doesn't add any new constraints. And then down here, we have a call to f with input y that's of type v. And so this is a little bit more complicated, but here we're going to just make a constraint that the type parameter, the type v needs to support whatever constraints there are on the input to f, whatever f is. To understand that a bit better, here's a deeper example. And what we need to do is, in step 2, to stitch together those different constraints for each variable and each type. We do that in 2 ways. First, if we have multiple uses of the same value in a function, values of the same type in a function, we simply conjoin their constraints. So here, for function f, we have postfix increment, prefix increment, and plus equals 1. And we encode this in the type constraint that the type t needs to support all 3 of those operations. For the second case, inside g, f is being called on the input x. But there are 2 different versions of f. There's the one that takes an integer, and there's the one that takes this generic type t. And so here we use disjunction to account for the function overloading. We say that U either has to be of integer type, or it has to fulfill all of the constraints on the types of inputs to the second function f, that is postfix, prefix, and plus equals 1. And then in addition, of course, here we also call x.print, so we conjoin the constraint that x needs to support the print operation. Finally, you can imagine that for large functions, these formulas get a bit unwieldy, and they can grow quite long if we have many uses of a variable with a generic type inside the function. And so we need to minimize these formulas. Unfortunately, minimizing arbitrary Boolean formulas is an NP-hard problem. And so in this work, we take the approach of doing an incomplete but fast algorithm, because performance is important in contexts like, for example, an IDE. And so we use an existing formula from existing work that has time complexity that's linear in the formula size and the nesting depth. So we've implemented this based on Clang and evaluated it on two benchmark sets, one algorithm from the standard template library and the other special functions from the Boost library. And the implementation is publicly available at this link, and you can also find that in the paper. We evaluate for 3 questions. The first of those is whether the synthesizer infers good interfaces. And to do that, we compare the constraints that are generated by the synthesizer to those that are given in the documentation for these libraries. This shows that example for the standard template library. And you can see that in this case, in every case, the synthesizer generates a constraint that is an over-approximation of that given in the documentation. So for example, if we look at the merge operation, we see that there are, the documentation says that this should be a triple with input iterator, output iterator. But our synthesizer says that all 3 of those should be an iterator. So it's an over-approximation. Yet you can see here that in most cases, it's a useful over-approximation. There are very few cases, just a couple, where we synthesize an any type where we don't know anything about the constraints. The second question that we evaluate for is how useful these synthesized type constraints are for the end users. And as a proxy for that, we measure the length of error messages that are given by the compiler if you try to call the functions improperly with inputs that don't match the type parameters. So for both of the cases, both of the benchmark sets, the average number of lines of error messages decreases substantially by more than half, and in the case of special functions, from 43 all the way down to 15. And you can see that graphically represented here as well. The blue bars represent the original length of error messages, how frequently they occur in each length category. And the green bars represent the length of error messages after constraint synthesis. And you can see that they're much more clustered at smaller lengths, and we don't have any error messages that are very long and difficult to interpret. Even for error messages that aren't necessarily shorter, we claim that they're more easily interpreted. So here's an error message from the Boost Math template, from the Boost Math sign function. And here again, we have this invalid operands to a binary expression that goes on for several lines that isn't very helpful for users who might want to understand what the problem is and how to fix it. After we synthesize constraints on the types, we see a much more useful error message that says that the constraints weren't satisfied. And from that, a user can go back, look at the constraint set, and determine what was wrong and try to fix it in a much faster way than they could before the type constraints were synthesized. And finally, in this work, we take a certain trade-off between the speed of implementation and the precision of the type parameters. And in this work, we've chosen to take the speed side of that trade-off. So you can see that the execution time of our approach is very fast. It's 1/4 of a second for algorithm. It's just over a second for special functions. And we've successfully synthesized non-trivial function type templates for hundreds of constraints, for hundreds of functions in each case, but clearly not for all of them. So in this case, we've made a choice that speed of implementation is more important in cases like an IDE, and generating precise constraints for every function is less important. But you could take a different trade-off and embody that in your choice of for a Boolean formula simplification logic and achieve a different result. So in conclusion, we studied the constraint synthesis problem for C++ function templates. This is particularly important for synthesizing templates in existing code bases with large functions that don't yet have function templates. We designed and implemented a constraint synthesizer that generates automatically these function templates, and then we evaluated it on 2 libraries from the standard template library and the Boost library, and found that it's efficient and it synthesizes useful constraints in almost all cases. With that, thank you very much. Again, you really should thank Shuo Ding, who did the work here, but I'm happy to do my best to take any questions.
So, any question from the audience? Yeah, please go ahead.
So I think it's a really good work, but I just have a small question. Like, actually in the C++ community, there used to be a proposal to do a similar thing to this. It's not about concept, it's about no except. So once someone wrote that you should write no except auto to actually let the compiler automatically deduce what the no except conditions are. But a problem found with that is that there are often some unintended syntactic structures. Like, for example, if you call a function, you sometimes need to implicitly call the copy constructor and some of that. I wonder, is that handled well in the constraint generator?
So generating the type constraints, I think, is more, it's at a higher level than in the compiler, right?
Yeah.
So it's useful not like in guiding the compiler, but more so in letting programmers build code that is correct and doesn't contain the errors, right?
Yeah.
So I think this is really at the source code level, and so it shouldn't change the behavior of the compiler at all.
Okay.
It's just providing stricter type conditions for the users.
So essentially, you're just injecting those required clauses onto the functions.
Yeah, the templates.
Have you considered actually assigning a name for the concept? Like, for example, if you detect it must support ++, it probably is an arithmetic type or something like that.
I don't think that's been addressed yet. It wasn't in this work.
Okay.
That's a good idea for future work, though. We might explore that.
Okay, thank you.
Hi, thanks for the talk. Katerina from Carnegie Mellon and University of Lisbon. You mentioned a little bit how you're measuring the error reporting being better with like smaller size messages and everything. Do you plan on having any developers looking at those messages and comparing how they are compared to the previous ones?
Yeah, that would definitely be a good next step. I think so far we kind of have intuitive examples of that, and we've used the error message length as the closest proxy short of a user study, because user studies involve a lot of additional design questions. But I agree that would be good future work.
Okay, thank you.
Okay, the second speaker.